Hello everyone, it's Dave Giles here for the next lesson of IGCSE Physics, Cambridge International Education. It's Unit P3 Waves, and today we're looking at TIR, or Total Internal Reflection. So today I want you to find the critical angle of a glass block by a calculation and describe the process of total internal reflection. So, as we looked at previously with refraction, when a light hits the boundary between two materials, the ray is normally bent or refracted. This happens because the speed of light changes in different materials. If the angle of incidence of light ray is greater than the critical specific value, called the critical angle, then the light ray is actually reflected. As you can see here, we've got light reflected out of a block. This is total internal reflection. One little note here, it's a semicircular block. So that means when the light hits it, it's always going to be at 90 degrees to the norm, which is why you don't see the bending in here. But you would still get this total internal reflection with a non-curved block. So it makes the inner surface of the glass act like a perfect mirror. So let's take a look at it. So you can see I'm shining a light in there, and got an angle of incidence, got angle of reflection. Just to be clear, we're talking about the angle of incidence here. Let's talk about that again. So this here is the angle of incidence inside the block, and then this here is the angle of refraction. And you can see it's because the angle of refraction is bigger because it's moving away from the normal. However, you reach a certain point, and now we're getting reflection. It follows normal reflection law of angle of incidence equals angle of reflection. And there will be a specific point, it's quite difficult to find exactly usually, where you will have the light going perfectly straight along here. So the light won't be reflected out. It won't be refracted out as well. It will go 90 degrees across here. So here is what I've shown you. So the angle of incidence is smaller than the critical angle. The light ray is refracted. And this is the one I was trying to show you earlier, but it's a little bit tricky. So here now the angle of incidence equals the critical angle for that block. Now every material will have a different value for its critical value, say critical angle. If the angle of incidence equals the critical angle, the light ray is refracted along the boundary 90 degrees to the normal. If the angle of incidence is greater than the critical angle, then the light ray is not refracted and total internal reflection occurs instead. So is the critical angle always the same? The critical angle is the smallest angle of incidence at which total internal reflection occurs. Different materials have a different specific value for the critical angle. So, for example, water 49 degrees, whereas diamond is quite low, 24. So this means the diamond reflects more light than other materials, which is why it's so sparkly when you look at it. So if you look at a diamond ring, you'll see light shining off in different directions. That is due to its low critical angle. So we can calculate the critical angle. Now you don't need to know how to derive it, so I will skip past that. So the main bit is skip this. So this is what you need to know. Sine of the critical angle is 1 over n, where n is the refractive index. So the critical angle is the inverse sine of 1 over n. So the inverse sine of 1 over the refractive index. Okay, this is a derivation which you can have a read through yourself, but you do not need to know this for IGCSE Physics. So a couple of quick questions. So for light is refracted and reflected, so which one is this referring to? So this happens when you have the angle of incidence is like that. is smaller than the critical angle. Total internal reflection takes place. So that's when the angle of incidence is greater than the critical angle. And finally, if the angle of incidence is equal to the critical angle, then light is refracted along the boundary. The diagram below shows a ray of light moving through glass, which diagram correctly shows what happens when the ray of light strikes the surface of the glass at the critical angle. Well, it's the one I said earlier was a little bit hard to get, but it's going 90 degrees across the glass block, so it's B. The diagram shows a ray of light in glass incident on the surface between the glass and air. What happens if the angle of incident is made larger than the critical angle for the glass? So if it's made bigger than the critical angle, then you only have reflection. So the answer is D. The speed of light in air is 3 by 10 to the 8 meters per second. The critical angle for light in transparent plastic material placed in air is 37 degrees. What is the speed of light in the plastic material? Now, you do need to maybe go back and have a look at the last lesson on refraction to fully be able to answer this question. However, I'll quickly describe how you would do it. Okay, so the calculation, just put it on the screen here, how to do it. So you need to work out n first. We need to work out the refractive index. We're given the critical angle, so we rearrange this to get n is 1 over sine of critical angle. So it's 1 over sine 37, which gives me 1.66. Now the speed of light in a material is the speed of light in a vacuum divided by the refractive index, which is 1.66. And that gives me 1.81 by 10 to the 8 meters per second. So the answer is A, two significant figures. So now we're looking at optical fibers, so more towards the second learning objective describing total internal reflection. So optical fibers are thin strands of solid glass about the diameter of a human hair. They can transmit light signals at high speed over long distances. They are widely used in communication, medicine, lighting, and as sensors. The first transatlantic telephone cable to use optical fiber, went to operation in 1988. So here's a place where we can use optical fibers. So you can see there, the light travels through perspex, rod, even or curves. So let's have a look at why that happens. So you can see that it's bouncing here, so you'll say reflecting here, reflecting there, and reflects all the way down. And it happens because of total internal reflection, sorry. A ray light enters the optical fiber. As the ray moves from air to glass, it is refracted. So this means that the direction of light is traveling changes. The ray of light hits the wall of the fiber and is totally internally reflected when the angle of incidence is greater than the critical angle. The ray of light passes down the optical fiber by repeated total internal reflection until it exits the fiber, where it refracts again at the boundary. And you can actually do a demonstration here where, and I've done it in my class, where you can shine a laser through a stream of water. So normally get a plastic bottle, put a hole in it, fill it with water. You can actually see the ray of light refracting all the way down to the bottom. So let's have a look at some places where it's used. So it's sent in the form of light signal from one end of the optical fiber to the other. The light bounces off the boundary between the core and the cladding. So the core is the bit in the middle and the cladding is the bit on the outside. This enables the light signals and hence information to be transmitted along the optical fiber. So now have a look at another application, which is medical use. So this is called an endoscope, where you can have a look, or in this case, it looks like it's actually going directly into the patient. An endoscope is fed in through the mouth. And you can also get a colonoscope where it's fed in through the other end. So one of the two main endoscope cables carries light from a bright lamp in the operating room into the body, illuminating the cavity where the endoscope has been inserted. Because obviously you're going inside the human body, it's going to be dark in there. There's no natural light. The light bounces along the walls of the cable into the patient's cavity. The diseased or injured part of the patient's body is illuminated by the light shining in. Light reflected off the body part travels back up a separate fiber optic. So there's two sets of cables. There's light going in and then light coming out, bouncing off the glass walls as it goes. The light shines into the physician's eyepiece so he or she can see what's happening inside the patient's body. So here's some quick questions. Does an optical fiber need to be straight for total internal reflection to happen? The answer is no. What happens if the angle of incidence is smaller than the critical angle? Then light is refracted. And answer the exam question to the right. Figure 1 shows how a ray of light from a laser travels along an optical fiber. Why does the ray of light stay within the optical fiber? Because the angle of incidence is greater than the critical angle. And then this exam paper question, each diagram shows light of incident on a glass boundary. The critical angle is 42 degrees. Which one of the diagrams shows total internal reflection? Well, it's the one where the angle is greater than 42 degrees, and you can see the reflection going on the side, so the answer is D. And the last little set of questions. The diagram shows an endoscope being used by a doctor to look inside a patient's stomach, light traveling into the stomach through a bundle of optical fibers. The sentences describe how the endoscope will allow the doctor to see inside the patient's stomach. The sentences are in the wrong order. Rearrange and start with letter Q. So light passes through a bundle of optical fibers into the patient's stomach. And then the inside of the stomach reflects some of the light. The reflected light passes through a second bundle of optical fibers. The optical fiber takes the light to the eyepiece, where the doctor looks through the eyepiece to see inside the patient's stomach. Then the last question, the glass prisms are used in many optical devices. The diagram shows what happens to a ray of light as it travels through a glass prism. Use the words in the box to help you explain why ray behaves this way. Light is totally internally reflected if the angle between the ray and normal angle of incidence is greater than the critical angle. Okay, the next lesson will be on sound, and I'll be uploading that to YouTube soon, and I will put the link in the description below. Thank you very much, everyone, and I see you later. Thank you, and bye-bye.